Bismillahirrahmanirrahim. So before the final, this is the last lecture. So in this lecture, we try to cover the term first Fourier transform, which is also known as FFT, which is nothing but the DFT with a fast algorithm, so that the computer can work faster whenever we need to process our xn to xk. So that is all about the FFT. In the later part of this lecture, we can discuss about the final exam if we have any question from the student side. Okay. Even before that, if you have any question from the previous lecture. It seems that you don't have any question at this moment. Okay. To understand the first Fourier transform, definitely you need to go back and forth of this lecture. I will upload this PDF with your video lecture, inshallah. So you need to go through this lecture at least for a few times to understand the whole things. However, the fundamental objective of today's lecture is to understand the algorithm, not to memorize any part of this algorithm. Okay, so be relaxed and make you understand the process, not to memorize any part of it. Okay, and in any part of this lecture, if you have any question, please do not hesitate to raise your hand. Okay, so we can start with the basics of the DFT. As we already know that this is the basic equation of the DFT, where this is our input signal and this is Wn, where Wn means this. We need to understand it for this algorithm, that if we are putting Wn is equals to e to the power minus j twice pi divided by n, then we can mention that if n is equals to n by 2, then this w can be notated as n divided by w subscript n divided by 2, because this number basically denotes this number. Okay, so this is the definition of DFT. Direct computation of this DFT is inefficient, and primarily because it doesn't exploit the symmetry and periodicity properties of the phase factor Wn. As we have already know that this Wn, that means this is the exponential term e to the power minus j twice pi divided by n, which is a combination of sine and cosine in the real and imaginary. So this is a complex term. It has these two properties. One is symmetry properties, another one is the periodicity. So we can exploit these two properties to make the DFT algorithm faster, and which is known as FFT. Okay. So the computationally efficient algorithms known collectively as first Fourier transform algorithms exploit these two basic properties of the phase factor. So there are several algorithms to make the things faster, and collectively these algorithms are known as first Fourier transform. So today we'll explain one of those. If you are interested, there are some books. We have the basic fundamental books for the DSP. We can also find different algorithms in the different book. But we will discuss the fundamental ideas, why this is faster and how faster it is. Okay. From the history, in 1965, James Cooley and Johann Tukey, so Tukey, So in short form, Cooley and Tukey, they have invented this first Fourier transform algorithm. Before that, if we have n samples, in that case, in conventional DFT, we need n square, in the order of n square multiplications. On the other hand, whenever the first Fourier transform has introduced, then these calculations becomes n log 2n. You can understand in the log processing, whenever the value is very high, let's say the log 100 gives the value is equals to 2. Log 1000 gives the value is equals to 3. So whenever the value is very high, comparatively, this number in the log, the result is very small. So in that way, whenever this n is very high, let's say 1000 or 10,000 or more than that, even this number of samples, then this is very efficient. If you compare n is equals to 2 or n is equals to 4, then it looks like, okay, it is not very efficient algorithm. But whenever n is equals to, say, 2 to the power 10 or something like that, or you can say 10 to the power 5, something like that, in that case, it is very efficient algorithm. Okay, with an example, we can understand how fast it is. Okay, let's say we have the number of sample is equals to 1000. In that case, in conventional DFT, it takes 10 to the power 6 mathematical multiplications. They need this number of multiplications. On the other hand, in the first Fourier transform, it takes 10 to the power 4 multiplication. It sounds not very prominent. However, if we calculate 10 to the power 9 is the value of n, in that case, in conventional way, this is 10 to the power 18. Whenever for the first Fourier, this is 30 into 10 to the power 9. From the time scale, if each and every multiplication needs 1 nanosecond, just 1 nanosecond for each calculation, then 10 to the power 18 takes 10 to the power 80 nanoseconds, which actually is equivalent to 31.2 years, almost 31.2 years to do the calculation. And if we look back to the FFT, in that case, it takes the value is equals to 30 into 10 to the power 9, only 9. And for this calculation, it takes only 30 seconds. You can understand you need 31 years, and comparing to the first Fourier transform, you can just need 30 seconds. And to be very specific, before having these first Fourier techniques, it is totally impossible to implement the DFT in the computer, because in case of the computer, if you need this amount of time, or for small segments of the sample size, 10 to the power 6 even, it takes a huge amount of time. So that's why this is not practically implementable whenever before finding the first Fourier techniques. So that's why, so in the last century means the 19th century, this FFT technique is one of the most important algorithm for the modern society. If we do not have this first Fourier techniques, we don't have the telecommunication, we don't have the internet facilities, and nothing else. Okay, so and the science and technology will definitely would suffer for this kind of algorithms. Okay, now how it is so fast? Okay, so what is the logic behind this? Okay, so we want to find out that story of the first Fourier transform. Okay, so I'll go back and forth So first of all, some theory, then example, and then again theory of the first Fourier transform. Okay, let's start with very simple notion. So this is xk. We know that what is xk. For today's lecture, I can also use it as fk. So fk, this k mentioned like f0, f1, f2, which is belongs to x0, x1, x2. Okay, so those are the same thing, and is equals to this, and we already know that this is the definition of the DFT. Now the first step is that if we have how many samples we have capital N number of samples. Now we are dividing these total samples in two frame, n by 2, where this shows the even numbers, and these takes the odd numbers. So for example, these even numbers, that means we have x0, x2, and so on. And in the odd numbers, we'll have, sorry, small x should be there. I'm talking about the input, x1, x3, and so on. Okay, whatever the numbers you have. Okay, need to be memorize this part, that what should be the value of capital N. There is a bindings. It should be the number of power 2. So it should be 2 to the power 2, or 2 to the power 3, 2 to the power 4, and so on. So, or 2 to the power 1. So that means the n could be is equals to 2, or 4, or 8, or 16, and so on. Okay, so it should be represented with the power of 2. Okay, the concept is, the first is we are dividing in two parts, n by 2, n by 2. This is even and this is odd. Okay, so we can represent in that way. Try to understand the total number is from 0 to n minus 1. So we are dividing in two parts. So we are taking the even part here. We are putting a dummy constant twice m, and e to the power minus j twice pi by capital N into k twice m, because we have this twice m. Now small n is replaced by twice m, and the range of m is from 0 to n by 2 minus 1. You can understand it. Okay, let me write it. For m equals to 0, then what will happen? You will get x0. For m equals to 1, you will find what? x2. For m equals to 3, you will find x. So 0, 1, 2. So for 2, it will be x4. So you can find that you are getting the even numbers. So you will get the even numbers. That is our target. And what is the maximum number? You should process what should be the maximum value of m. If we took, for example, if we took n is equals to 16, so the maximum number of m should be n by 2 minus 1. So that is 8 minus 1 is equals to 7. That actually gives you the half of the portion. So for 7, we'll get we get the number 7 into 2, so 14. So we'll get all the numbers in the bucket of the even indexes. And the other section is, so we can write in this way. So x, okay, let me discuss it first, and then plus the odd sections, odd numbers. How we can represent that? This is twice m plus 1, and e to the power minus j twice pi by capital N, k twice m plus 1. Everything remains the same, just a dummy constant will play the fact. Here the m is again from n by 2 minus 1. And if you put the value of m equals to 0, you'll find x1, m equals to 2, you'll find x3, m equals to 2, you'll find x5, and so on and so forth. So what we have done, everything looks like the same, but we are dividing two parts. Let's say Fk can be represented as Fk even plus Fk odd. That is the thing we have done. Very simple. And why we are doing this? Okay, that is one of the questions we should ask. First of all, if we have n numbers of the samples, and if you look at this equation, just concentrate to this equation, how many multiplications you need? You need basically n square multiplications, because you have x0, x1, x2, and up to xn, capital N minus 1. So how many samples you have? You have n number of samples. For the n number of samples, you need to multiply n number of Wn, isn't it? Because for all the numbers, you need to multiply the Wn with the coefficient of e to the power j twice by n into k and n. So different for Wn, you have kn. So for x0, it should be multiplied with Wn to the power kn. You need to put the value of k and n, of course, but you need to multiply that. So this is one multiplication. For x1, again k and n, second multiplication. In that way, how many multiplications you need? You need n squared multiplication if you have n number of samples. On the other hand, what happens if I divide in two sections? In this case, how many multiplications you need? Because you are dividing in two sections, it needs n by 2 whole square plus n by 2 whole square. And now you can understand that it actually reduces the overall multiplications with a huge margin, not a huge margin, but at least with a higher value when the value of n is high. So let's calculate that. This is n squared by 2 plus n squared by 4. Sorry, it should be 4. So then we can have 4. This is n squared. You can find that this is 1/4 of the previous one. So the total multiplications is now reduced in that way. Okay. So what we have achieved with this even and the odd indexes, we can reduce the total number of multiplication, and that is our objective. Okay. So why we are doing this? To reduce the answer is to reduce the total number of multiplications. Okay. Okay, need to be more focus on this topic. Okay, so no need to memorize any part of it, just try to understand that thing. Okay, now elaborating that the previous section. Okay, we are doing the same thing. This part is for the even, and we have done it. This is for the odd. Okay, so here what we have done here, of course, there is twice m, there's some mistake, and in the later section we are doing twice pi. This is what we're doing here. Okay, so in this equation you can find, if you are looking at this, you have 2 there. So these 2 can come to n by 2. So if it is n by 2, in the other section, in this section, what we can also do, we can also take common of 2. So and then we can put this 2 there, and that's why there would be 1 by 2. So we have done the things here. So this is not included. Okay. So you can find that x twice m e to the power minus j twice pi divided by n by 2 into km. On the other hand, for the odd function, this should be twice m plus 1 e to the power minus j twice pi divided by n by 2 into k m plus 1 This is 1 divided by 2. Okay, so just correct it. This is 1 divided by 2. Okay, we are just proceeding with that fact. It remains the same for the even. For the even function, it will remain the same. And for the odd, what we are doing, just compare this. There are two terms, e to the power j twice pi by n km minus, it should be plus, sorry, into multiplied with e to the power minus j twice pi divided by n by 2 into half. Okay, because we have another term over there. So we are finding that term. We have this extra term. And if you consider that we have this extra term from this to this, we are taking exactly the same thing here. Okay, nothing has changed there. What we are doing, if you can look at this term, in this term, there is no m value. So it is independent. This function is independent of m. This is only dependent with the value of k, and capital N is constant. So what we can do, we can take out of this summation, and that is logical. So we can take it out of the summation, and this is that. And for a particular value of k, it is constant. Okay, we can define it by ck. Okay, now this is the final equation we have found. Let me zoom it. So you will find the final equation looks like this, where we have sector our total n in two sections. One is even and another one is odd number, where we have n by 2 and n by 2 numbers for each segment. Okay, so try to remember this equation. Not remember means memorizing the things. The fact is that this is for the even, so fk even, and this part is for fk odd and multiplied with a value ck. Okay, so this is the whole process. This is a phase factor. Of course, this is a phase factor which has already defined in this equation. Okay. Okay. Now what we have found here, we have sectorized our even and odd function. Okay, and please, whenever I will upload this PDF, this is page number 5. There's a mistake. After page 5, this is 7. So actually this is 7. So we need to move to page number 6 before 7. So this is page number 6. And now what I am doing in the page number at the end of the page number 6, the 5, we have found some terms, and you can, if you can look at, you have this common term. You have these two are the common term. So these are the common values. So now we try to understand deeply how these terms looks like. This is the term. Okay. Okay. In this term can be written as a cos function with the sine function. So very simple. And what is the range of k? The range of k is from 0 to n. Try to understand the range of k is from 0 to n. So how many values you should find for fk? How many these terms you should find? You should find n numbers of this term. Okay. for k is equals to n by 2 plus r, or you can say r is equals to k minus n by 2, where r is equals to 1 to n by 2 up to the half of the total segment. What we can write, we can replace the k value with this. Let k is equals to this. Okay, now we are replacing this k value for the cos segment. We are taking only the cos segment and we are putting that. And after deriving the things, okay, just go through the derivation. It's very simple. We have found this, and from there, what we can say, since m is an integer, always this is an integer, and the range of n is from 0 to n by 2 or n by 2 minus 1. And as I have already mentioned, then n should be a power of 2. So n should be a power of 2. So let's say a to the power 2. So always whenever you are dividing it 2, that will generate an integer. Okay, no problem with that. So for any value of the integer, this doesn't make any sense. So it will give you the full cycle. So twice pi, twice pi, thrice pi. So in all the cases, it will actually rotate the full cycle. So whatever we have found here, we can write that this is equals to that value. So we start with the function cos. If we can remember, we start with this, where we can put k is equals to this. If we put k is equals to that, even though we can return it to that value, it shows that for k is equals to n by 2 is the period of that function. So for this function, k is equals to n by 2 is the period, because after n by 2 we have got the same value. Okay, I can write the things again. E to the power minus j twice pi k m and divided by n by 2 is equivalent or equals to the value of minus j twice pi. If you put the value k is equals to, what is the value? We are putting k is equals to n by 2 minus r. Okay, in that case, we have found this value. We come back to the original value. So that what we have found here. Okay, repeating the things again. We start with this. We put the value k is equals to that, and putting that value and doing all the mathematical calculations, what we have found that the result looks like this. Okay, so when we add any value with k is equals to n by 2, then it repeats. So that means n by 2 is our period. So that has been shown here. N by 2 plus r. So n by 2 is vanished. That means it shows that this is a period. Okay, like if we have t, let's say n0 is equals to n0 plus n. So that means n is the period of that time scale. So similarly, cos this function is equals to this function. We have proven that. So that means n by 2 is the period of this cos function. That means the period of the value of k. So for the k, that is the period. So this is also true for the sine function. We can prove it for the sine function as well. So if for the sine function and cos function, n by 2 is the period, then of course we can say that for this function, n by 2 is also the period. We have shown it for the sine function. We have shown it for the cos function. So that means it is obvious that for this function, the period is n by 2. Okay. Now we have already mentioned these two lines before. Okay, it shows that they are period. Okay, now we can jump to the page number 8. So we have, and that shows the symmetry identity. So that means after n by 2 samples, everything looks the same. And we have that experience before, because according to the DFT, what we have found, let's say we have found the symmetry after n by 2 samples. Whatever you have there, so you are getting the sample back and forth after you have the repetition. So you have the repetition, you have the repetition, you have the repetition. Okay. So as we know that this is k after n by 2, we have the repetition. Always we have the. So what is the period here? We found the period is n by 2 for this kind of function. So k, now we can say that the k runs from 0 to n. However, everything repeats after k is equals to n by 2. So after n by 2, it actually repeats the thing. What you have, it will repeats the whole factor. So the total number of operation is effectively half. Of course, that will makes the things faster. This identification makes the things faster. Okay, so what we have learned at this moment up to now is that we have fk, and we have decided to divide in even and odd, sorry, k odd, and of course there is a ck value, that means a phase factor. Now what we can do, this even function can be again divided in two parts, and this odd function can be again divided in two sections. And in this way, this can be divided in two sections, and this can be divided in two sections. Up to which ladder we should go? That is the question. The answer is up to two samples, up to two samples in a bucket. So in this bucket, whenever we have only two samples, only we have two samples, up to then we need to proceed. Let's say total we have 16 samples. So even and odd, we have 8 and 8 samples. Now we have 4 and 4 samples. Here we have 4 and 4 samples. Need to divide it again. We have 2 and 2 samples. We have 2 and 2 samples. You need to do it here. You need to do it here. So whenever you have only 2 samples, up to that you need to extend this segregation. So that's why, just to understand the fact, we just take the even function, even part. So we have already discussed it in the earlier section, and now we are dividing these things into two sections again. So in this section, what are the samples we have found? X0, X2, X4, 0, 1, 2, 3, 4. Let's say X6, X8. Let's say we have 4 samples. Now we need to divide these samples into two sections as well. So how we can do that? Again, we already put the dummy constant m. So let it take it here. So x4m, where m is from 0 to n by 4 minus 1. Okay. And of course, here this should be m, this should be 4m, where this 4 now turns to, given here, n by 4. Okay. You need to care about this. So what are the samples we are targeting here? For m equals to 0, this is x0. For m equals to 1, this is x4. For m equals to 2, this is x8. Okay, good. For the other section, this is the new ck for this one. In the similar fashion, you will find that x 4m plus 2. Here x 4m plus 2, and e to the power minus twice j pi k divided by n divided by 4. Okay. And of course, for this plus 2, there would be this value. Okay, we'll get this value. Okay, to do it yourself, you'll find that. What are the samples we are targeting? For m equals to 0, we got x2. For m equals to 1, 4 plus 2 is x6. For m equals to 3, sorry, 2, for m equals to 0, for m equals to 1, for m equals to 2 is 8 and 10. So x10. Let's say x10 is our last sample. So you can understand previously what we have, we have x0 up to, let's say, x10. Just to understand the things, we also have x1, x2, and so on. From there, what we have done, we are taking x0 up to x0, x2, x4, and x10. And we have the odd numbers are in another bucket. Now we are dividing this even function in two buckets. In one bucket, we have x0, x4, x8, and so on. And on the other bucket, we have this x2 to x8, x10, x2, x6, and x10. What is the advantage? I have already mentioned that in the previous section, we have n samples and we need n square multiplications. If we divide it n by 2 and n by 2, in that case, we need n square by 4 multiplication. Now, if you divide it again, so then it will be n by 4 and n by 4, n by 4, n by 4. Then what are the, how many multiplications you need? You need n by 4 whole square plus n by 4 whole square plus n by 4 whole square plus n by 4 whole square. And if you look at that, you'll find that it will be n square divided by 16. So now it is the total multiplication is now downgraded again more and more. So if you are dividing the sections with the even and odd more and more, definitely it will downgrade it, the total multiplications. That is the fact. Okay. I have given one example here. I will not do each and every part of this example. This is your known example. However, you need to go through that by using the equation. Every part has been given here, described here. Okay, so if you can go through this, you will find it very convenient. Okay, so we have taken 1 hertz signal. The amplitude is 1 volt. Okay, you can say 1 volt. And the sampling frequency is 4 hertz. So the total number of sample is 4. So very simple example. We have done it earlier. So those are the samples. The value is 0. Here is 1. There is 0, and this will be -1. Okay, this will be -1. Okay, for this section, what we try to do here, it looks a little bit messy, but this is the way how we can discuss the things. So this is the fundamental equation of the DFT. From there, this is, you can now understand, this is the even, and this part is from the odd. And again, we are divided this even function in the 2 other section. This is the section, and this is another section. How long we should divide that? For our section, you can understand we have total n is equals to 4. So in one bucket, we have 4. That should be divided in 2 and 2. So if you divide in 2 and 2, that is enough. Okay, so you can divide in just one scale down, and then you can find these two points. So we have even function and the odd function, and just putting the value of 0, you can find this is equals to 0. And for putting the value m is equals to 1, m equals to 2, m equals to 0, we have this is equals to x2. And what are the values? You also understand what are the values are there. from the graph, you can find those numbers. What we are doing the Fourier transform, but in this case, we are using the first Fourier transform algorithm. That is the difference. So this is the first line. This is the first line for finding the FK. In the second line, we are dividing it in the two segments. So this is again FK. And this is from there, you can find the value for x0 for this section. For this section, you have x2. From this section, you have x1. And from this section, you have x3. Don't confuse with this term. This extra term basically came from the value, like whenever we are putting this twice m plus 1 or 4m plus 1, then from this one term, this extra term came here, and that can be represented as ck. Okay. Okay. So now this is the total equation. So the total equation belongs to this, where we have all the four terms: x0, x2, x1, and x3. If we can consider this equation, now you can find the value of f0. This is f0. Putting all those values, you can find that this is x0, x2, x1, and x3. Why that is so? Because for f0, whenever we are putting fk, now put the k is equals to 0. That means we are looking for f0. What happens? This k is equals to 0. This k is 0. If e to the power, if we have 0, then e to the power 0, and it belongs to 1. So then we have only x0 there. Similarly, k is equals to 0. So this will be, sorry, this will be 1. This will be 1. This will be 1. And this will be 1. It has been written there. So all the exponential term will be vanished. That's why what you have found, f0 is equals to x0 this plus x2 plus x1 plus x3. Okay, straightforward. And now you can find the value. Yes, x0 is equals to 0, x2 is equals to 1, x1 is equals to 0, and x3 is equals to -1. It has been already given in the sign signal. We know that. So from there, you can find the value of f0 is equals to 0. You have got this. You need to note it down. Okay, so this is the value of f0. Okay. We need to memorize, or we need to think about this. For k is equals to 0, we have found this, and this is the note. For any value of k, these are equivalent. You can find that this is this can be written as 2 into twice pi. Of course, after twice pi and twice pi, that will repeat. So that's why they are same. And this is equals to 1. It is equals to 1 in case of k is equals to 0. We have already mentioned that. However, they are equal. They are equal. These two terms are equal, even though they are not equals to 1. This is only true for k is equals to 0. However, for any value of k, they are equal. So in the previous equation, this term can be also replaced with the value of e to the power minus j twice pi k divided by n, because 4 pi and 2 pi, they actually give you the same value. Okay. Now looking to this one, this 0 means the frequencies, the component k is equals to 0. f0, this 0 means k is equals to 0. And the upper notation e means for the even function. So even function means 0 and 2. From there, we got f0e is equals to 1. And f0 odd function, if we concentrate on x1 and x3, the summation gives -1. Okay. we can note it down. So three things we have found: f0 is equals to 0, f0 even function gives 1, f0 odd function gives -1. Of course, this summation should give this final result. Okay. We can write it down. f0 even is 1, f0 odd is equals to -1, and f0 is equals to 1. Okay. Now what about f1? So in the previous equation, just put the value k is equals to 1. Whenever you will put it there, you know all the values, and we got this result. This one, 0 plus 1 into 0. So pardon me, this result should be 0. This should be 0. And then minus j, this part actually came from this phase factor, and this is 1, and this is x3, and from there this is a constant. By putting the value k is equals to 1, and what is the capital N? Capital N is equals to, for this case, this is equals to 4. So you'll find -1. So altogether, this part will produce 2. This is f1. This is for k is equals to 1, and this is for odd summation. It gives 2, and there is a minus j. That's why the total number is a minus twice j plus 0. That will give total value is equals to minus twice j. So we can note it down. f1 is equals to minus twice j. What is f1 even function? f1 even function is 0. f1 odd function, what is the value? This is equals to 2. You need to understand. We have found these numbers. This is for f0. This is for f1. Okay. Now we found the result for n equals to 0 and 1. You can say that n equals to means for k is equals to 0 and 1. Okay. We have found this result. Now, what is the total number? The total number of n is equals to 0, 1, 2, and 3. So where is n by 2? This is your n by 2. So if you have already found f0 and f1, that is, you are at the location of n by 2. We have already found that. Now it will repeat. After n by 2, everything will repeat, isn't it? Everything will repeat. So that's why no need to do any sort of calculation anymore, because if we do for 0 and 1, we can derive it for 2 and 3. And now we can see how to derive those things for n equals to 2 and n is equals to 3. So now this is the process. Based on that previous example, we can write it. Of course, we know it. Okay. How we can know that? Because as I already mentioned that e to the power j 4 pi by k by n, it can be written as twice pi by k. So they are the same function. So from the previous equation, full equation, you can write like this. You can understand for k is equals to 2 and for k is equals to 3. This 3 is that and this 2 is that. This is even and this is odd. Okay. We need to keep these right side equations so that we can understand. Now what is our target? Our target is to find F2E, F2O, F3E, and F3O. Do you have any clue that where we can retrieve those things back? Is there any information we already derived? Yes, we have already derived those information. And let's see that. So we have found that this from the equation, you can, if you go back to that, you'll find that f0 and f2 definitely after n by 2. So 0 plus n by 2, 0 plus 4 by 2, that is 2. So that means 2. So f0 and f2, they belongs to give the same value. So for the even function, for the odd function, for the even function, 1 plus n by 2, that is 1 plus 2 is equals to 3. So that means 1 and 3, they have the same value. So we already know if f0, let's say f0e, where is that? f0e was 1. So we know that. That means we already know what is f2e. We know f1e. This is f1e is equals to f1e is equals to 0. So that means we know f3e. I believe you understand. Similarly, if you know f0 odd is equals to -1 is equals to f2 f1 odd is equals to 2 is equals to f3 odd, because they have the symmetry. So based on that, again, what I have mentioned, whenever you have found f0 and f1 with f0 even and f0 odd, f1 even and f0 odd, that means you can also find f2 and f3 completely. You do not need to do any sort of processing, because you know already those values, and that actually saves the time and the multiplication, and that is the clue. And by doing that, you can go through this calculation, and at the end you can find these 4 values: f0, f2, f1, and f3. And you can see that, okay, I have plotted the magnitude response, and you can see it there. Okay, so this is the example we can perform. Okay, the other part, please go through this. I will not discuss this at this moment. Okay, please go from there. There is a butterfly structure. There is called butterfly structure. 8-point butterfly structure can be asked whenever we have x0 to x7. So how many samples? We have 8 samples. So how we can present them? So first of all, always we should look at the simplest number, then we can move to the other one. So for example, we can take n is equals to 4. For that one, we have derived this. Just go through this terminologies, and you will find it. I have given you the result part. Okay, so the capital X0, it means that X0. Okay, X1 means X1. It actually been a function of xk. So for that one, we can derive like this: x0. For x1, we can derive it like this. For x2 and x2. If you can look at these numbers, we are also printing some value like a0. What is a0? a0 equals to x0 plus e to the power minus j twice pi 0 by 2 into x2. That is your x0. We need that afterwards. And what is b0? This is x1 e to the power minus j twice pi 0 divided by 2 into x3. Similarly, we have x1, this is a1, and this is a b1. We have mentioned that. Okay, and x2 is equals to, previously we have already mentioned a0, so this is that a0, and this is a b0. Okay, only this multiplying factor is different for x2. Similarly, we already defined A1 and B1, only this multiplying factor is different. Okay. Now only for n equals to 2, we can write these equations like this. We have x0 and we have x1. How we can represent it for understanding, let's say with these two equation number 1 and 2, just draw this diagram. Okay, maybe a little bit zoomed that. Okay, so try to understand the fact we are putting 2 points. One is x0 input and x1. Those are the inputs, and from there these are the two outputs. One is capital X0, capital X1. This is in the time domain and this is in the frequency domain. Okay, so that's very simple. Now, of course, to find the x0, we need those two information, small x0 and small xm. So from this equation number 1, we can find it. So to find the capital X0, what we need? Small x0 multiplied with 1. So straightforward, it can go there and multiplied with 1. What do we need? Again, x1 multiplied with this. And this is nothing but W2. You can find that n is equals to 2. Of course, this is W2 to the power. What is the value of k? K is equals to 0. So what we can do, we can take it like this, and this is W2 to the power 0. Okay, fine. Similarly, in equation number 2, to find x1, what we need? X0 directly multiplied with 1. Okay, so I have taken it like this and multiplied multiplied with 1, and the second section is x1 but multiplied with what? Again W2 to the power 0, but there is a minus. Okay, and as you can see that this looks like a butterfly. That's why this is called a butterfly structure. Okay, so this is for 2 points. Now if you increase the number, it looks like the same. So this is the small butterfly. First of all, this is the small butterfly, and you have 2 small butterfly first, and then this segment will goes to that value, and this segment goes to that value. So no need to memorize the things. First of all, you need to write the equation, and from that equation you can understand the fact. So try to make the major points here. This is in the time domain and this is in the frequency domain, in the DFT. Our target is to find the DFT value. Okay, so if you just look at how to calculate this x0, I can write this straightforward by this example. X0, capital X0 is equals to x0 because it actually multiplied by 1 and 1. Okay, then what we need there? We need plus, this is x3 multiplied with W2 to the power 0 into x3, and again that is multiplied by x W4 to the power 0. So again that is multiplied by W4 to the power 0. I believe you understand. So this process shows that you have some straight line. You do not need any multiplications. Similarly, in many cases, you have this kind of straight line where you do not need any multiplications. So like this one, you do not need any multiplications. And that sort of jump actually save our time in general. Okay, so how to put these numbers? there is a logic how to put this number. First of all, why this is x0, then x2, then x1 and x3. Since you have, of course, you have this number like 0, 0, 0, 1. So I'm writing in a chronological format of that one. So this is 0, this is 1, this is 2, and this is 3. And now do the folding operation. So 0, 0, this is 1, 0, this is 0, 1, and this is 1, 1. So this belongs to x0, this belongs to x2, this belongs to what? x1, and this belongs to x3. In that way, we can start. Okay. So first synchronously write the number and then swap the numbers in between. Just flip it down. So first value goes to the last value. So the mirror image. And then what is the number it represents? That is the sequence of these numbers. Okay. You can follow the book, and you can do it for capital, sorry, n is equals to 8. How it can be done, I'm giving that. This is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, and so on. So whenever you are swapping the things, so 0, 0, 0, this will be 1, 0, 0, it will be same, 0, 1, 0, this will be 1, 1, 0, this will be 0, 0, 1. So that shows that it is x0, this is x, what is the number? 0, 2, what is the number? This one, 4. This is 4, this is 2, this is 4 and 2, 6, and this is x1. So in that way, you can find the left side. What are the sequences? Of course, you can find that x0, x4, x2, and x6. These are the even number. Similarly, you can find the odd numbers in the later part of that. Okay. In the last section, I have shown that calculation. I have already given the hints that this n number can be given as even number and odd numbers. So we need that sort of multiplications, and we need extra. So this part was missing in the previous section. We have extra multiplication of this ck. So how many multiplication? N by 2 times multiplications. Okay. So the total multiplication looks like this. The total multiplications. I'm not sure whether I have missed that. It should be, yeah, it's okay. N square by 2 plus n by 2. That is the total multiplication. Previously, it was needed n square. So definitely this is downgraded. Now, if you are dividing more, so the example is given. So if that is n by 4 square plus n by 4 square plus n by 4, this is for that constant, n by 4 square, n by 4 square, and n by 4 for that constant. So altogether, we need these multiplications. In that case, in that way, it will be multiplied, more downgraded with the value. That means you need log to a scale n. So that is the multiplication order of this. And previously, it has actually needs an order of n square, which is actually been so efficient and fantastic algorithm, and which is known as the fast Fourier transform. Okay. Okay, so what you need to do, you need to skim through this whole lecture and try to understand the process. The fundamental or the key point is why fast Fourier transform is faster than the conventional DFT. That is the fundamental question you need to answer. If anywhere else you need, it might ask in the interview or other process. You do not need to memorize the things. You need to know the steps, how how to derive the process and other things. Okay, I will upload this PDF file with your video lecture, inshallah. Okay. Any question from this part? Of course, you should have a lot of question, or there might be some confusion. So what I believe that you can please go through this lecture. Still, if you have any question, we can arrange some extra time so that I can discuss with the matter if you have any confusion. Okay. Okay, I believe you can go through this and can understand the process. Okay, now quickly I can discuss on the final exam. First of all, this is of course an online exam, and this is open book. This is open book exam for you. As I always believe that you need to understand the process, not to memorize the things. Okay, so if you can understand the process and you can take the notes, okay, you can at the end of the day, I try to figure out whether you understand the process. It's not this class is not to memorize the things, because in future if you memorize the things, it will not actually help you. If you understand the process, you can search it in the internet, you can search it in the book, and you can implement that in your research career or in your job life. So that's why I try to put the question in such a way so that you will find it very easy if you understand the process already. Okay, and the syllabus already you know the syllabus after the meet to today's lecture. That is the whole syllabus. There should be 3 questions, 1, 2, and 3. All are mandatory to answer. And since this is the open book exam, the wrong answer or the wrong idea will not be accepted. So be careful on that, because you have the advantage to justify your answer with your notes or with your knowledge and any part of that. So yes, you can take the help from your book and notes and other sources. But this is the reminder: you are not allowed to take any help from any person, specifically with your from your friends, and that is very, very punishable problem. In an open book section, you are not allowed to discuss anything. You can take the notes and other things, and it is not very difficult to find out the persons from whom you are getting the help. I believe that you will not do that. But even though if you have done that, and it will be, and if that will be found out by the invigilators and basically from myself, that will turn out to be a very dangerous decision for you. Okay, so don't do that. You need to understand the process, and hopefully that will help you. So all 3 are mandatory. One by one question will be given. You will get the question, and it is actually been the copy type prototype of the midterm. So you'll get the question, you'll get some time to return it. If you found it problematic to return it in time, just send it via email, and of course it should be sent it to my official email, taslim@iut-dhaka.edu. Okay, so to this email address, not to any other email address. Okay, so only there. And even though you have sent it to my email, after that you should upload it to the Google Classroom. Okay, so you have to upload it to the Google Classroom when even if you have uploaded to my email address. Okay, so, and you can expect a very prominent portion from the Z transform and the filter design part. That is, of course, that is a core part of our syllabus. However, the discrete Fourier transform and the Fourier transform, they will also carry some numbers. Okay. The filter design is the most prominent part of our syllabus. Okay. And all-pass filter, the group delay, and the linear phase, non-linear phase, Z transform, and the filter design, the concept. Okay, those are very necessary. Okay. That is everything from my side. If you have any question, we have two minutes more to discuss the matter. Okay. So then, I hope you all the best. So thank you very much to you all throughout the semester. We have actually tried to understand the process honestly. That is our main focus, and by the evaluation I try to understand who are those students that have understood the process of the DSP, and hope you all the best for the future. And I believe if you like to continue the journey with the signal processing and other things, which is very important for the modern career design for the electrical engineers, you may also join to the filter design in the next semester. Okay, so probably we'll have, of course, we have the Viva session after the final as well. So inshallah, we'll see there in the next Viva session. And by this time, if you have any combined question, so we can arrange a short meeting before the exam, inshallah. So thank you very much for your participation.
Sir, one question.
Yeah.
Sir, if you could publish the marks of mid and quiz, then it would be better for ourselves to know ourselves.
Okay,
Better for us.
for the midterm, it is not possible for me at this moment. And for the quizzes, quiz I would try, because your last quiz is still pending. What I believe that before having the last quiz, I shouldn't publish the previous marks, so that you have the energy to give your last quiz. Okay, I try to publish the first quiz and the Viva marks after having your last quiz. Okay, I try to do that, but for the midterm publication is probably a bit difficult for me, so probably I can't publish that. Okay. Okay, thank you very much. I don't have any more time. Thank you for your participation. Thank you. Assalamu alaikum.